3 more seconds. Okay, we're good to go.
Okay, so welcome everyone to the QISS virtual seminar. Today, we are very glad to hear Lucien Hardy. If you have questions during the talk, feel free to ask them during the talk by unmuting yourself. Of course, then the speaker is allowed to postpone the answer to the end if you like it. Okay, so Lucien, I'll let you speak.
Great, thank you. And thank you for the invitation. This series of seminars has rapidly become my favorite series. It's great to bring together these different communities. So I've been obsessing over time symmetry for the last 6 months. You know, since I'm working at home, my children have to hear a lot about it. They're my main collaborators nowadays. And so last night, my 8-year-old daughter drew this picture. You can see it here. So time symmetry and time symmetry drawn backwards. Yeah, let me just begin. Okay, so just a few remarks. So first of all, you know, abstract probability theory is just about calculating things like the probability of X given Y. And as such, it knows nothing about time. And that's been a point of view that you know, I've tried to elaborate or knows nothing of causal structure even. I've tried to elaborate in the causaloid framework. And I think many people have looked at this like causally neutral formulations of quantum theory and so on. And more recently, other papers that I'll talk about. In operational probabilistic theories, such as many people have been working on in this community, in the quantum information side of the community, they concern probabilities associated with circuits. Now, the circuits themselves are kind of time symmetric, like the pictures, but the time asymmetry comes in because of certain conditions, mainly the condition that future choices don't influence probabilities in the present, and then correspondingly, there's a mathematical thing that deterministic effects are unique. Quantum theory at the level of the Schrodinger equation is time symmetric, as we know. The quantum theory of measurement, which is sort of at the root of these operational theories, can be treated without any reference to the second law of thermodynamics by a very simple model. Even though in real measurement instruments, thermodynamics will be playing a role, there exist simple models which capture all the essence of the theory of measurement that where thermodynamics doesn't seem to play any particular role, and so it seems like it shouldn't be relevant at some level to the theory of measurement. There are lots of different arrows of time. You know, the thermodynamic arrow being the main one people talk about. But I think what's happening in quantum theory is we actually have a cognitive difficulty pseudo arrow of time. So it's not a real arrow of time. It's similar to the problem that it's very easy to say the alphabet forwards because we've learned how to do it, but it's cognitively quite difficult to say the alphabet backwards because we haven't really learned how to do that. And my contention is that the arrow of time in quantum theory is similar. It's simply hard to think backwards in time because we're not used to it. So I'm in the process of learning how to think backwards in time in quantum theory, and it's quite hard. I was also trying to learn how to say the alphabet backwards, and there are lots of YouTube videos that you can watch to do that. Okay. So here's a statement. So, well, the first statement isn't provocative. We cannot signal from the future to the past. That's something everyone knows. Second statement, also, we cannot signal from the past to the future. That statement seems more provocative, but in a certain sense, we'll see how that is true. However, we can steer information in either time direction. Okay, and I'll come to that later. There's lots of work on time symmetry, and here's a small sample of papers. So the classic paper is the ABL paper on time symmetry, gives a time symmetric formulation of the sort of pure state version of quantum theory. There's a paper by Bob Kirk and Lau, Raymond Lau, on time symmetry. There's a paper by Silva et al., which doesn't talk about time symmetry, but it is meant to be a sort of density matrix version of the pre and post selective formulation of ABL. So probably there's an important message for time symmetry there. There's the fascinating paper by Oreshkov and Cerf, which I haven't fully digested, and I think it would probably plays a role in some of the remarks I have to make towards the end of my talk. And then I especially want to draw your attention to this recent paper by Di Baggio, Donna, and Ravelli, who I think are all here, at least I've seen Andrea and Carlo, of course. So this is a paper came out last month, Quantum Information in the Hour of Time. So much of what I'm going to say finds counterparts in this, this paper, including the provocative statement I made just before. So at this stage, a lot of things I don't want to especially make any claim to originality, because I think a lot of it's already in this paper. Some of the presentation is different, and perhaps some of the points towards the end of the talk are going to be more original. But I do encourage you to look at this paper. I should also say that my own thoughts on the subject were strongly influenced by a presentation that Andrea gave back in May. So here's this is the first slide to that presentation. Okay, so but this I'm going to start. I take my own starting point. So let's think about operational formulations of quantum theory. The basic object in an operational formulation of quantum theory is an operation. So these are the sort of boxes that you wire together in order to form a circuit. So, and here's the standard notion of an operation in quantum theory. So we have some inputs down at the bottom and outputs at the top. And these are your physical systems, like in quantum theory, they're your quantum systems, but this is a more general notion, so they could be something else. And then you also have, coming in from the side, you have the settings. So these are the choices, the knob settings, and so on. And these are classical. And then you also have the outcomes. These are things like detector clicks or pointer readings, and these are classical too. And that's the standard notion of an operation. And I must have drawn a picture like this in every paper I've written for the last almost 20 years, and every talk I've given, almost every talk I've given for the same time period. But this standard notion isn't actually fit for purpose. We need to change this standard notion if we're going to take time symmetry seriously. So let's just look at this notion. So we can see it's not time symmetric because the outcome is something which is available after the measurement. But the settings are available both before and after. Okay, so here we have a time asymmetric diagram. It's clearly not time symmetric, but it's also clear what to do to make it time symmetric. We need to add something, and the thing I'm adding is called an income. I'm using the word in a different sense than it's normally used in the English language. Normally it refers to finance, but I think historically it was used in this sense as well. That's something that comes in. So we have now incomes as well as outcomes. So incomes are available in the context of the operation itself. Incomes are available before, but not afterwards. In a broader context, you can imagine copying the classical information of an income and porting it around so you can make it available afterwards. But that's some extra structure that you put down It's not relevant to the operation itself. Yeah, so incomes are also classical. And I was pleased to see that some people strongly disagree with this. This was incidentally some of the protests that resulted because of the in the UK, the announcement of the high school qualifications was done by an algorithm which tended to favor people from higher income backgrounds instead of based on the teachers' projected grades during the pandemic. Okay.
Question.
Yep.
Is income something you choose? Is it like a setting, or is it?
Let me come to that. There's
something you get from your parents.
Yeah, I'm going to come to that shortly. There is clearly a crucial distinction between incomes and settings, and I think this is something that I think that if you listen to what I say, it'll maybe make more sense. But I think it's a notion that needs to be refined. In fact. Okay, so. Yeah, so here, incidentally, the settings, for the most part, I'm going to be interested in incomes and outcomes. So I'm going to take the setting part of the diagram to be implicit. So I won't draw that arrow. And then it's useful to use this sort of notation. So I'm going to denote the incomes and outcomes by this sans serif font, by the types, by X's and Y's. So these are the types. And then they'll take values which are integers up from 1 up to n sub x, 1 up to n sub y. Okay. So I think this might answer Ravi's question a little bit. So you can build time symmetric operations, and particularly refer you to the paper of DiBaggio et al. In this. So a time symmetric. So here's a way of doing it. So what you do is you have some systems coming in at the bottom here. I'm realizing if I point to the screen, you can't see that. I have to use the cursor. And some systems going at the top. And then here you have an income type, which is attached to a box that prepares incomes in a corresponding maximal set. In quantum theory, it's a basis. And likewise, you have the same thing over here. And so incomes might be things like initial pointer states chosen from a maximal set. They might be initial ancillar states chosen from a maximal set. And outcomes are things like final pointer states and post-selection, if you post-select on something. So here's a slightly more general notion of a time symmetric operation. Here we have some of the incomes and outcomes. We have an R box. So R corresponds to a flat probabilistic distribution in one direction. Or if you consider it in the opposite direction, it corresponds to the ignore box. So here's a more general, this is really the most general sort of thing you consider. I want to put some, there's going to be a few red flags during the talk. And so I'll highlight them. So here's one of the red flags. It's a bit odd that we're considering a flat distribution, because that's a rather particular distribution. Why don't we consider some other kind of distribution? But nevertheless, this seems to work if you consider flat distributions. Okay. So now we can draw a circuit, or we can wire these boxes together. So here's the boxes wired together, and I've wired the systems, the physical systems together, and I've left the income and outcome types open. And if you look at this circuit, what you can do is you can collapse out all the quantum systems. So you end up getting down to this box I've drawn on the right. And here it just has all the incomes over here and all the outcomes on the other side. This box M is a classical box. It has classical incomes and classical outcomes. although there is physics, maybe quantum physics, depending on if you're treating quantum theory or some other situation hidden inside the box. So, yes.
I've got a question. Hi.
Go ahead.
I'm wondering, in your previous diagram, what is a pointer state?
So a pointer state, if you have I don't know if you're familiar with the von Neumann model for measurement, but typically you have a quantum system that's prepared usually in an initial pointer state, and then you have, and then you subject it to some interaction with a quantum system, and then afterwards it moves to a superposition of final pointer states, and then you collapse onto those pointer states to see what the outcome is.
Okay.
So it's a reference to the von Neumann model of measurement, which you'll find in the literature. Does that answer your question?
Yeah, thanks.
You're welcome. Okay. So where was I? Yes. Okay. So we have this box M, which has all the information about the incomes and the outcomes, and we've collapsed away the quantum or the physical systems. And so now we can take that box M with all these things, and we can write it down like this, as I've done on the right-hand side, where we just use this notation where U represents all the incoming or the incomes, the composite income, and V represents the outcome. And so here's a very simple classical situation. We have a box M, it has some income and some outcome. But this classical situation holds the key, I would say, to understanding time symmetry in operational theories, such as quantum theory. Okay, so I'm going to give you 5 double properties. The word double is being used because we have 2 directions of time. And if you're going to be time symmetric, we want these properties to be the same in both directions in time. And these are the 5 properties. And I'll go into them in more detail in subsequent slides. So probabilities add up to 1 in both directions. Seems reasonable. That's double determinism. Double flatness, a flat distribution in gives a flat distribution out. So if you send a flat distribution into that diagram from the left, you get a flat distribution out from the right, and vice versa. Double causality, this is what I was referring to at the beginning. We cannot send information in either time direction. Double relaxed bistochasticity. This is a mathematical condition that results from the first 2 conditions. And double distribution uniqueness. I'll come to that if I get time, but there are kind of unique pairs in this that sort of fit together in this situation. Okay. Okay, so double determinism. The word determinism may be confusing to people who aren't in the sort of operational quantum theory community. So just ignore it if it's confusing. Really, it's just the condition that the probabilities add up to 1. So I guess the 1 is the determinism. So it's the condition that the conditional probabilities of, so the probability for this box of getting a particular outcome given a particular income, if you sum over the outcomes, you should get 1. So there's the condition, and we want the same condition backwards, like that. Okay. Double flatness is the condition that if we send a flat distribution in to the box, then we get a flat distribution out, and also vice versa. So we have forward flatness, which is one direction, and backwards flatness, which is the other direction. And we demand this is true for maximal sets of incomes and maximal sets of outcomes. The word maximal is sort of important because you want to have the most finely grained set of incomes and outcomes to make this statement, because coarse grainings, if you take a fine-grained situation, then you perform some coarse graining. Of course, you can turn a flat distribution into a non-flat distribution. Okay, so oh yeah, sorry. Here's the forward direction. So you send a flat distribution in, you get a flat distribution out. Here's the backwards direction. You send a flat distribution in from the right, you get a flat distribution out.
Lucien, may I ask something?
Yes, go ahead.
So what are you describing here? Is it a definition of a type of operation, or is it a desideratum of some sort?
Okay, so this is a property that you can demand that M has. Okay, it doesn't have to have this property, but you can demand that it does have this property. Or you can demand that a collection of M's have this property. Okay. Okay. So it's a property you can demand. Okay. And later on, we'll see that quantum theory has this property. And I should say there's also in the work of Divaggio et al. You'll see these notions there as well. Okay, so just here's the mathematical condition of forward flatness. So if you send a flat distribution in and you work out what you get out, then you want that to be flat as well. So that gives you a condition on the sum of these conditional probabilities here. And there's also a condition for the backwards flatness, a similar condition. Okay. Double causality. So forwards causality is the property that there's no access to information about M. So this is a property. There's no access to information about M from the outcome without some knowledge of the income. So if I want to determine by looking at V information about what M I have, whether I have M or M prime, then I need to have some knowledge about what I send in. No knowledge is the case where you have a flat distribution. So if I have a flat distribution coming in, then I cannot read off any knowledge about M from V. That's the property of forward causality. The property of backwards causality is the same thing, but in reverse. And so if we have double flatness, then we have double causality. Okay, that's clear because if I send a flat distribution in, if we have double flatness for all M that we consider, then we have double causality. So if I send a flat distribution in, then I get a flat distribution out, regardless of what M I have. Okay, but it could be that I send a flat distribution in and I get a non-flat distribution out, but I get the same non-flat distribution for all different boxes. Okay, for all different M. So that could happen. That would still be consistent with double causality if it's true in both directions. So whilst double flatness implies double causality does not imply double flatness. Okay. I wanted to put a red flag on the sort of flat distribution thing here. The fact that we're assuming that the no knowledge situation is the flat distribution is something we can question. Perhaps our no knowledge state should be some other distribution, like a thermal distribution. Okay. So here's an example of double causality. So here we send, we have, this is the backwards case. So we have some income coming in. We have a state, a basis preparation. We have a box W, then we have Y measurement onto a basis, and then we have the flat, the R box, which is the flat distribution if you look at it in the backwards direction. Everything that happens here, the X, W, and Y can be regarded as can be collapsed into an M box. Okay, so that's just like the previous examples. And that's just equivalent to the flat distribution over the incomes. So so we get no information about W, because if we try to read off information on X, it's just equivalent to the flat distribution. We can also argue here that we have a unique deterministic effect. I won't go through that argument. And here's the same thing in reverse. Now we're trying to read off information about W in Y. But for the same reasons, we can't read any information off about W from Y because it doesn't matter what we put here. If we have forward causality, then we can't read off this information. We can also, sorry, it's also clear here that we have a unique deterministic state. Okay, so what we see is we cannot signal into the past or the future. So we cannot find out information about a process W in the future without some knowledge of the past. Okay, if we have a flat distribution coming in, then according to the double causality property, we can't read off information about W. And the same is true in reverse. We cannot read off information about a process W in the past without having some knowledge of the future. So in some sense, we cannot signal into the past or the future. However, we can steer. So if we do have information in the past, we can, if we take some of that information forwards, then we can use it to read off information about W. The situation, sorry, I meant to do a diagram here. The situation is very analogous to the situation in entanglement theory. So if you have an entangled state and you make a measurement on one side, you don't change the distribution over here. But if you condition on the outcome of that measurement over here, then you can look, then you will see a different distribution over here, depending on the different values of this outcome. So for different outcomes on one side, you'll get different distributions over here. So you can steer information in some sense between the two ends in an entanglement type experiment. And likewise, in the situation I'm discussing, you can steer information in a forward direction, which is what we do typically because we have memories, but you can't steer information and you can steer information in a backwards direction, which is not something we do typically, but you can think about situations where that would happen. Okay. Oh, and here's another red flag. We have here a maximally entangled state because the actual case we're going to have is if we have this double flatness, then the state we actually get, then it's analogous to a maximally entangled state because we have, maximally entangled state is one that has a flat distribution on either side if we trace out the other system. And if we have double flatness, then it's like having a maximally entangled state. Okay, so what I haven't shown you yet, oh no, I haven't shown you yet that this works for quantum theory, but I will show you that. Before I do that, I want to just discuss one more thing, which is what I'm calling relaxed bistochasticity. So if you search on the internet for non-square doubly stochastic matrices, then you'll find this paper. And so the definition of a non-squared doubly stochastic matrix or bistochastic matrix is that the rows have to add up to a constant sum, and also the columns have to add up to a constant sum, but those two sums don't have to be the same. So if you have a bistochastic matrix in a normal sense, then the columns have to add up to 1 and the rows have to add up to 1. But there's a generalization of that idea, which is that that the rows add up to a constant and the columns add up to a different constant. In this paper, they called it doubly stochastic with quotation marks, but it's difficult to say that. Like maybe you have to use a sarcastic voice when you say it. So instead, I'm going to call it relaxed bistochastic. Okay, so relaxed bistochastic matrix is one that has this property. So yeah, so the case where you have a square matrix is just the usual case of a bistochastic matrix. And another property is that these relaxed bistochastic matrices, they compose in parallel and in sequence. So if you put two bistochastic matrices sort of next to each other in parallel, then you get a sorry. You talk to relaxed bistochastic matrix, and if you compose them in sequence, likewise. Okay. So it turns out that the properties I've shown you, the property of forwards determinism, forwards flatness, and backwards determinism, backwards flatness, give you a relaxed bistochastic matrix. So the matrix whose entries are the conditional probability V given U is a relaxed stochastic matrix because of these properties. And the matrix whose entry is probability of U given V is also a relaxed bistochastic matrix. This follows if we have the property of the properties of forward determinism, of double determinism and double flatness. So hence we have the property of double relaxed bistochasticity. So this is the mathematical condition, and this encodes double flatness, and it also encodes double determinism, and it implies causality. Okay. So now let me show you how this works in quantum theory, for example. So quantum theory has all the double properties I've just discussed. So here's a circuit. And then I'm going to replace each of the elements in this circuit by a build, like the builds I showed you at the beginning. Okay, so here's an example. And now I'm going to take this diagram and I'm going to distort it. So, okay, I've brought, let me just show you, I've taken all the small boxes down to, at the bottom, down to the bottom of the page, and all the small boxes at the top, up to the top of the page. Sorry. So I have this diagram. Okay. And the unitary operators have been isolated. They all appear inside this red box. So now what you have is a situation where you have a whole bunch of systems coming in, prepared in some basis state, and a whole bunch of systems coming out. And so if you consider the case where there's no R boxes for the moment, then the probability of V given U is given by this formula here, which is equal to this formula, which is also the probability of U given V. And you can see this is bistochastic because if you add over U, for example, then by linearity, you get the identity inside this trace. And likewise, if you add over V, you get the identity inside here. So this is a bistochastic matrix. And this point is made in the paper of DiBaggio et al. And now these R matrices themselves are associated with double bistochastic matrices. They're just rows whose entries are all equal to 1. And so if you compose them, then you still have a double relaxed bistochastic matrix. Okay, so so quantum theory has the property that it is the mathematical property that it is that you get these doubly relaxed bistochastic matrices for the conditional probabilities going forwards or backwards. Okay.
Sorry, can I ask a question at this point?
Yes, go ahead. Yep.
So if I remember correctly, at the beginning you had boxes with incomes and outcomes, but
yeah.
Did you also have a system entering? No.
Yeah, oh, so the very beginning, yes. So I can go back to, I'm worried to lose my place. So at the very beginning, I had boxes. So let me just go up a little bit here. So here, for example, take the A box here. It has a system coming in and a system coming out. It has an income and an outcome. Okay, so that's an example. And then I can wire them together so all the systems, or the physical systems get, so there's no physical systems left open. Okay.
But can you guarantee that when you do this, that the remaining evolution on the incomes to outcomes remains unitary?
Okay. I think what I'm saying is that in quantum theory, this is the sort of way you would build a box like the sort of box I was showing. And so then the diagrammatic manipulation from here to here shows you that you can isolate this unitary part. Okay.
Okay.
So so it's just in quantum theory there's all these theorems about being able to any operation you can extend it, so you have a unitary operation and some ancilla and so on. It's this appears in the paper of Di Baggio. You can just you can sort of have a time symmetric formulation of that, and that's what I'm doing. Okay.
Lucien,
yes, go ahead.
Is 5 minutes enough for you to finish? I'm just watching.
Yeah, I was also watching the clock. Well, let me just see what I can. Yeah, I think I can finish in 5 minutes. Yeah.
Okay.
Like a relaxed double stochastic 5 minutes. Yeah.
Cool.
Okay. So so that's the yeah. So quantum theory has all these double properties I presented so far, which means that it is doubly. It has double causality, so you can't signal into the past or the future in the particular sense I was referring to. Okay, here's another double property. I promised 5 double properties. Double distribution uniqueness, and this is the one that's given me the biggest headaches, but I think I understand it now. So here's a situation where we have some distribution prepared going in. And I'm going to, just for the sake of writing down these properties, I'm going to read out the U value and read out the V value. And I also have, so I have an E box, which prepares, if I read it in the forward direction, a distribution going in. I have an F box, which prepares a distribution going backwards in time. So in the forwards time direction, I can write the conditional, sorry, I can write the joint probability of U and V like this. And in the backwards direction, I can write the conditional probability of U and V like this. So these are 2 different ways. And these equations are, if you equate them, you get Bayes' theorem for relating conditional probabilities. In fact, here's the equation. And we can do the same thing now instead, where I just put primes on E and F. I'm keeping M the same, but I put primes on E and F. So I now take these 2 equations I've got at the bottom. Here they are. And I can divide them as long as the conditional probabilities are non-zero. And if I divide them, I get this. And now, using double determinism, you can show this means that actually the primed and unprimed distributions in and out are unique. Okay, so this just rely on this condition here, but that seems like a condition that will be true for a lot of times. So that's kind of shocking, because surely you can send any distribution in and get some distribution out, and then if you just send that distribution the other way, everything should be consistent. I guess I don't really have time to talk about this in detail, but there are some sort of secret assumptions going on in proving this theorem, but I think they're good secret assumptions. So we do have so we have this strange property that actually the distributions that work in this sense are a unique pair. Okay, and you can relate this. You can look at this and compare it with the statement of forward causality. So forward causality is the statement that if you send a flat distribution in, the distribution you get out is independent of M, and you have the backwards causality version of that as well. But if we want to have distributions like this in and out that match, so if we have a matching pair, then actually we need to have a flat distribution. So so double causality in conjunction with this double distribution uniqueness gives you double flatness. But like I say, there are some secret conditions that I haven't talked about. Okay, so the flat case is the unique causality respecting matching. So this is the case that respects that matching I was talking about. Okay. Right. So just this is research that and this part of the research is most of what I talked about before. You'll find counterparts in the paper of Di Baggio et al. So this is something that I'm doing, which is new, but it's under construction. And so I'm just going to talk about it a little bit. So this idea of conditional frames. So there were lots of red flags. I talked about before. Let's see. So double causality and double flatness do seem to go together. But instead, we could define causality with respect to deviation from a non-flat distribution. So then we'd have a different notion of causality. So if we did that, we would want to have, rather than having double flatness, we'd want some different property. So perhaps we could usefully consider different pairs of distributions that come in these unique pairs. And if we did that, so the question arises is, might the doubly flat case be analogous to an inertial frame of reference? Okay, when you see the word flatness and you think about general relativity, it naturally makes you think about inertial frames. Perhaps there's some analog between the flat case I've been discussing and inertial frames of reference. In particular, perhaps we can transform to a non-flat frame in some appropriate sense. Then the question is, would this resolve all the red flags I've been raising throughout the talk? And how would quantum theory look in a non-flat frame? And should we be concerned only with quantities that are invariant under these transformations? So I don't have answers to all these questions. It's just the beginning of a research project. But here's an idea of what a conditional frame of reference might look like. So the idea is that typically when you do an experiment, your laboratory, there's a lot of stuff that you have to condition on, and if you have a quantum optics laboratory, I worked for many years at La Sapienza. Sorry, for 1 year, I worked at the Sapienza University in Rome in the experimental group of Francesco de Martini. And it was very important, that you pull the blinds down when you're doing a quantum optical experiment, and you have to get the thing isolated. So when you do an experiment, you are conditioning on stuff that isn't of immediate concern, and this conditioning is represented here by these two outer, the E and F, and then the experiments in here. And so the idea is that perhaps you can go to a more general notion of conditioning, which deviates from the flat case. Okay. So let me come to some closing remarks. There's lots of areas that to be worked on here. So one important question is the question of porting classical information around. So you have these incomes and outcomes, and if you want to be able to send information forwards in time, you have to take information from the past to the future, which means you're porting around this classical information, and there's a structure to this porting that I think is very interesting. Oh, sorry. There we go. I'm interested in developing this general theory of conditional frames. There's work I've done in the past, the Dewar tensor and operator tensor formulations, which those mathematical formulations were in a sort of time asymmetric framework, but they should naturally lend themselves to this time symmetric version. Also, there are certain physicality conditions on operators in quantum theory. So, most naturally, these are things like complete positivity and so on, and that operators should not increase the trace. And so these conditions will be replaced in a time symmetric theory. There's been a long research program on trying to find axioms for quantum theory that many people who are in the audience have worked on. I've always felt that there was something time asymmetric about those axioms that was unsatisfactory. And so perhaps if we can think about time symmetric axioms, we'll find a better reconstruction. And I know from the notes that Di Baggio, the talk he gave back in May, that he's thought about that somewhat. Okay, this no signaling result I think is interesting, and it's something that we can talk about. I think the interpretation of that is interesting. And then finally, and perhaps most importantly, will this help with quantum gravity? So my hope is that that by understanding time symmetry, we'll have a better road into quantum gravity. You know, general relativity is time symmetric, and so it makes sense that we want to have a time symmetric understanding of quantum theory. Okay, and I'll stop there.
So thank you very much, Lucien, for your talk. Unfortunately, Zoom is not very well adapted to applause, but you can imagine the 90 people attending your conference applauding you loudly. And now we have time for discussion. I will first let the discussion be initiated by a couple of questions by Ravi Kunchval. So Ravi, if you want to unmute yourself, then you can ask the questions to Lucien, and then we will have free discussions with all the participants.
I'll stop the share, I guess, for the time being.
Okay. Hi, Lucien.
Hi.
Thanks for the talk. So I was, I'm a bit overwhelmed by the amount of information in the talk, but I'm trying to understand, like, if the whole formalization of your talk is time symmetry and operational theories. So is this essentially an operational formalization of the von Neumann model of measurement in quantum theory in some sense? Because can I always interpret incomes as initial pointer states and outcomes as final pointer states, like without loss of generality in this approach? Is that what you're going for, or is there something more that you're getting at?
So I think so. In a kind of operational approach, for example, the characterization of if you take in standard quantum theory, standard operational quantum theory, you have a trace non-increasing completely positive map, and you can prove that you can implement any such map as long as you allow yourself just using unitary dynamics, as long as you allow yourself access to an ancilla. And that's very much a time asymmetric notion. You prepare the ancilla in some initial state, and then you do the usual dynamics. So it's not just a pointer state. The ancilla state is also important. But yeah, so it's not just the pointer state is important and the ancilla state is important, but they're both examples of this notion of an income. Which normally we allow ourselves to set some initial state without thinking about it too much. But actually, if you're going to understand quantum theory in a time symmetric way, you need to elevate them to the same status as the outcomes.
Right. So there are three things here: the system, the ancilla, and the pointer. Right. Like those are and the ancilla and the pointer is what you take to be like your incomes, for example, like the initial states of this.
Yeah.
Okay. So for example, when you I was trying to understand in particular, like, of your 5 double principles, like the one on double causality was the one I was kind of thinking a bit about, and I'm trying to understand if this is about so you have some classical variables like U, and let's say in the past there is some process M, and then you have some classical observations like, let's say, V in the future. And double causality is about being unable to learn everything about M using only information about V, for example. Like you also need something about.
He has to learn anything about M. Yeah.
Anything. Okay.
Yeah. Yeah.
Okay. So I was wondering, to what extent is this condition can you interpret this as a lack of some sort of like a screening off, like M is not really screening off U and V, like it's not the case that everything I want to infer about V can be inferred from M alone. And
okay, so I mean,
because there's a notion of a past and a future here. So if you imagine like I don't know, like if M, you imagine M is like something like on a space like hypersurface or something, and then there's a future and past. Like is this about like that? Like I cannot infer everything about what's on this surface from just like information of the future, or like what's going on here?
So what's important for this property is that you have a flat distribution over the maximal set of incomes. So any income that you have in the situation, you must have a flat distribution over it. Otherwise it doesn't work. So so usually the situations we consider, we sort of secretly are conditioning on something that goes into the box, and that's where we're able to read information. I see Carlo vigorously nodding his head, so I think I'm on the right lines. So we condition on just on something that goes into the box, and so we can read it off going out. But so we have to learn, in order to be able to think in a time symmetric way, we have to learn to be able to identify what these incomes are and have a flat distribution over them.
Right. So you want to you want to essentially collapse that flat distribution to some specific point, and that's your kind of steering kind.
So if your steering is
steering you were giving.
So anything which is non-flat may give you information. So if you have a distribution of incomes, but you make it slightly non-flat, sorry, you just jump to a different place. There you go. Sometimes the Zoom windows rearrange themselves, and the person you're looking at is somewhere else. So yeah, so anything which is non-flat may coming in may enable you to read off information and pattern. Of course, it depends on what M and M prime you're comparing. But yeah.
Okay, right. So I think I just forgot that the double causality condition was predicated on the fact that you have flatness of like U and.
I mean, the normal situation we're considering in quantum theory is where we have a specific value of U coming in. So normally we condition on a particular point of state, not a classical mixture of point of states, and we condition on a particular ancillar state, and we don't think about preparing a flat distribution over them. And in that case, of course, you can read off information about U and V, and that's fine. But if you want to think in a time symmetric way, then you have to learn to think of this flat distribution. I'm saying these words, I want to point people to the paper of Di Baggio, where there's a discussion, maybe not quite in the same terms I've given, but similar enough.
And how does this relate to your, like you're trying to draw an analogy with steering and with like a maximally entangled state, like local measurements on a.
Yeah,
can you elaborate that on, because this sounds a bit like you're referring to that analogy right now when you say that you pick something non-flat, like.
Yeah, so we're very familiar with the situation in entanglement theory, where if you have two particles, two systems in entangled state. Let's take the maximally entangled state case. So then either system is the distribution is flat, if just locally, and if you make a measurement on one side, you don't gain information about the other. You cannot read off that. You cannot read that off on the other side. It's only if you send the result of that measurement to the other side that you can steer the distribution so it becomes non-flat. So I think so this analogy, I think it needs to be further explored. It may just be an analogy, or it may actually be it's the same thing in a different guise. So I think there's a future research project in that.
Do you see an obvious connection here with like the Choya-Minkowski kind of picture, where you want to transform a channel into like a state?
That would be the way to proceed. If you were going to pursue this analogy, I think you would have to, that would definitely be a starting point.
And I guess,
but I haven't pursued it myself yet.
So in that sense, this should be related to the Oreshkov and Cerf sort of approach as well, right?
Maybe Oreshkov can comment on that when he comes here. But are you referring to the
25th, the time symmetry and operational reversal, time reversal in quantum?
Okay, yeah. So maybe we'll wait for Onion to comment on that when he gets the chance.
I actually was just away from my screen for a minute. I least actually.
No pressure.
I have questions which are probably related to that. Can I go ahead, or is anybody in?
So yeah. So if you have finished with your questions, Ravi,
Yeah,
then
I mean, I'm
suggest
happy
that we
to.
open.
Yeah.
Okay.
Yeah.
And I suggest that we open the discussions. There are already 5 hands which are raised, so I suggest that we proceed according to this list first. So first on the list is Alexei Greenbaum. If you want to unmute yourself.
Yeah, thanks. Hi again, Lucien. Thank you.
Hi.
Yeah, I'm very sympathetic, of course, with this approach. And I have 2 quick remarks. I think if you look at this problem of going beyond flat distributions, one way to do that would be, so things you mentioned at the end that you want to solve. One way would be to look at relational entropies of these distributions. For that, we have all the mathematical instruments needed, so you can forget flatness and just have conditions on relational entropies in both directions. So that's one remark. And another remark, is sort of an open question, would be, if you think about, let's say, the CHSH inequality, to formulate the CHSH inequality, you just need information about what you call incomes and outcomes. These are classical bits that go into the box, or even a PR box. So somehow one would be, wondering whether your language should already allow us to speak without adding more elements to that language, already allow us to speak about situations when correlations between incomes and outcomes obey certain bounds, on the polytope, because you don't need to say anything to be able to formulate that question.
Yeah, okay. I don't know how to think about it. One has to be careful to distinguish between settings and incomes. So in a if I can just draw a diagram here, in the okay, I'm just going to work. Okay, so here's a sort of Bell experiment, and S is the thing that prepares your let's say it's a maximally entangled state, but a maximally entangled state is not something in order to prepare that you need to pick out a basis state. So here at the bottom we have this income, which picks out the basis state. And then we have outcomes over here. So this is the correct diagram to discuss Bell type experiments within the situation I'm within the kind of framework I'm talking about. And so yeah, so I don't know, because you need this notion of income as well. And so now
if you look at if you look at entropic's Bell inequalities, then maybe it will be more symmetric, but I should stop because there are other questions.
Yeah, I'm always nervous about any entropy measures in physics because it has these logarithms in them. And A, I don't like logarithms, but B, they always refer to a sort of asymptotic kind of limit. And so you have to ask yourself if you're actually referring to the case where you have many copies or not. But yeah, I mean that's I mean I am talking about having knowledge or lack of knowledge, and so that it does naturally lend itself to these sorts of quantities. Okay.
So indeed there are many questions. So if I try to keep track of the order in which the questions the hands have been raised, Lee, if you want to ask your question.
Lee, you're still muted.
Yeah.
Yeah.
Yes, this is a very simple question about the logic of the argument, Lucien. So you begin with a situation where in many formulations of quantum mechanics, at least, there is a time asymmetry associated with measurement or the von Neumann projection or a collapse of a wave function in a physical collapse model, or et cetera, et cetera.
Yeah.
And you're coming to us and you propose that there can be an operational formulation of quantum mechanics which is symmetric in time. And you seem to demonstrate that, and other people also are demonstrating that. But if there is somebody who wants to maintain the view that time asymmetry is fundamental to quantum mechanics, and that the difference between being unresolved or having not being actualized is something that has to do with the future, or however you formulate it, your conclusions don't contradict that possibility. There's nothing you've done that says that there's any less reason for somebody to take the view that time in quantum theory is asymmetric, if we choose to.
I mean, so I'd say so if that's your point of view, I guess there's the sort of the good news and the bad news. So the good news is this is a way of looking at quantum theory where you can ask those questions about the time asymmetry you want, and contrast them with these sort of various properties. So it's good to have something to measure your ideas against. And the bad news is that you can formulate the theory in a time symmetric way, even when you take into account this. We knew that already from the paper by Aharonov, Bergman, and Leibovitz, but now we have we're doing it in a fully operational way, so it's an even stronger statement. And of course, also if we go beyond quantum theory, maybe quantum gravity will be time asymmetric, or maybe some subsequent development will be time asymmetric. I think it's good to have a clear formulation of how the theory is time symmetric to have something to work against.
Sure, sure, but we agree.
Yeah.
I understand correctly.
Yeah, I mean, it just I know that the paper I keep referring to, they have some discussion of different interpretations of quantum theory in there. I don't see if Andrea is. I don't see where he is on the screen, but
yeah, I'm here.
Yeah. I'm not sure. Do you want to give an answer to Lee's question as well, because you had that section in the paper where you discussed different interpretations.
Yeah, actually, we were just exchanging an email about it just before the presentation. Also, thank you very much for the acknowledgement. It's fantastic to hear that you were impressed by my work. I'm very impressed by your work. But yeah, we were talking with Lee that the argument cannot disprove that there is a fundamental time orientation, obviously, but it does show that it's not necessary to understand what we see in the lab. Beyond, I mean, you still need the entropic time orientation, but beyond that, you don't need to add another layer of asymmetry.
If we proceed on a list of questions, next is Tian Zhang.
Okay. Hello.
Oh,
hi. How you doing? Hi, good to see you.
Thanks for the nice talk. And I have a few questions. The first one is, in your previous figure, the system has input and income, output and outcome. And it seems to me that the income and outcome are part of the system which satisfies the double determinism and double flatness. I'm wondering that if we consider a whole system with also with, for example, with input and output, for example, a global past and a global future, whether they will obey these double symmetries. And it seems that only part of the system holds for this double symmetries in time, but not the full system.
I'm trying to understand your question.
Yes, I'm just wondering that how what's the input and output will be if they are inserted in your systems, because you are only consider if, for example, a global past and a global future.
Okay. Are you thinking in a sort of like a generalistic context or something like this?
Not really. I just wondering that if we have if for this system, if we have because in your figure we can only see the input, income, and outcome, But in the first figure, you show that you put also income, input and output. I'm just wondering this input and output, how will they play in this symmetric picture?
I mean, the idea is that if you want to calculate probabilities, then you generally the physical systems, the inputs and the outputs, you close them so there's nothing left over. Okay, so you draw a box actually. So the example I just showed you, like this, I have I've closed all the vertical wires are closed, and there's nothing left over. And so then you can just look at the sort of classical probability theory over the incomes and outcomes. So that's the idea on how to do this. Yeah, I hope that answers your question. If not, maybe we can talk more later.
Okay.
Yes.
And another question, maybe. I'm also wondering that when you discuss about double causality, it seems to me that causality is about cause and effects. It seems your definition about causality seems to be the information will not influence. If we, for example, the forward causality is if we have no excess of the income, then we will have no excess of the process from the outcome. It seems to me it's more like it doesn't exclude the possibility of the causal relationship. It's just something more like no signaling, not about causality.
I think so. Here's the situation I've been considering. So here I'm sending a flat distribution in, and I have m, and over here. So over here is the effect. The cause is changing m. I can do m, or I can do m prime, and those are different causes. So I can change my m, which is basically changing the setting. It's the arrow I suppressed, and I can't see that over here if I send a flat distribution in. So it is very much cause and effect, and this is the forward direction. You can also draw a backwards direction diagram.
Okay.
Okay.
And another question is about if you assume the double flatness. I'm wondering that it is a very strong assumption here. I'm wondering if you mentioned in your ongoing project you want to do some non-flatness work, but I'm wondering that I try to imagine how to work on that, but I have no idea. Could you share some ideas?
So I think so. The idea is I raised the idea is so my daughter also gave me this. She got it from a dollar store. It's very useful. Okay. So I had a diagram like this at the end. Okay, and you can put different this thing around the outside, the E and the F. You can imagine changing that to a different one. And when you change it, you're going to get the idea is that you'll be conditioning, like on this W down the bottom here, that you condition on. So you'll be conditioning on different stuff happening around the outside. And in so doing, you'll perform a transformation on the probabilities. So this is just an idea. I have to, I started writing down some equations, but the basic idea is that when you change this box around the outside, you deviate from flatness because you're conditioning on something, and so yeah. So that's the idea. That just that you can transform to different conditional frames by conditioning in that way. Yeah.
Thank you.
Okay.
Robert Eckel, would you like to ask a question?
Hi,
hey, Robert.
Thanks. Hi, Lucien.
Hi.
Nice talk.
Thank you.
Great to have you here.
Yeah.
Yeah, I have a question or a comment. So as you know, I've been working on the formulation of quantum theory that's not only time symmetric, but also could even be time agnostic for some years. The positive formalism in particular that you're certainly familiar with. So from that point of view, I have some question or yeah. So this is about trying to go another step. So I think in your perspective, when you were talking at the end about maybe going towards quantum gravity, what one would like to do is see this step from time-oriented formalism to a time-symmetric formalism as a first step, right? And so in that direction, yeah, let's say a word of caution, because so there's a certain problem with that from the perspective of the positive formalism. You can see that. So yeah, so I like to put this in the open here, that maybe other people could also look at this and see how one could make progress on this. So basically what happens is, if you look at general formalism, so if you get rid of time altogether, which you can do, and are completely time agnostic, then generically the operations that you have don't have all these nice properties that you introduced. In particular, they generically don't necessarily have forward or backward causality. In fact, you can't even say what that's supposed to mean, because you will not have a distinction between incomes and outcomes, right? So in the time agnostic version, in and out, everything is on the same level. There's no a priori distinction what is in and what is out. You just have these exterior connections in terms of the diagrams. And so then generically, as I said, you don't have these properties. Now in quantum theory, what you can do then is you can say, okay, so now I introduce a time direction or a notion of time. So I distinguish in and out. And then as you're saying, in quantum theory, what you can do is you can purify, and purifying, I mean, adding the ancilla systems, basically achieve that the interior is unitary, as you showed in various diagrams, and in this way achieve both not only forward but also backward causality. However, from a time agnostic perspective, the problem with this is, of course, that you need a notion of time to do that. I mean, even if, I mean, in your case, you're symmetric in the sense that the condition is valid in both directions, but you're still having a distinction of a notion of time. So if you give up this notion of time, then you can no longer say what forward or backward causality are. And so then your problem becomes, so basically one of the upshots of your talk was saying, well, quantum theory has these properties, and that remains true in the time agnostic situation, in the sense that in the moment that you distinguish in and out, I mean, even either way around, doesn't matter, then you can purify, and you can achieve a formalism that has both of these properties. However, there doesn't seem, or I'm not aware of a notion of purification that would be time agnostic. So this would be a kind of a hurdle in trying to push this further in the direction of general covariance and going to a general relativistic setting, as far as I can see. So my question is, I don't know if you've thought in very far in this direction, but maybe you have some idea about addressing this, or some perspective on this that you could share with us. So that's basically my question. Thanks.
Right, yeah. So, I mean, first of all, of course, I like your positive formulation very much, and also the preceding work on general boundary formulation, which raises a lot of these questions too. So my current thinking is the following. So in the sort of language I would use, the problem is that when you put quantum gravity so when you put general relativity and quantum theory together, you get indefinite causal structure. And so you cease to be able to talk even about, whether a particular separation is space-like or time-like, let alone whether it's forward or backwards. Kind of indefinite causal structure just messes all that up. And so you enter these kind of wild lands where it's really difficult to see how to proceed. And so the idea I have for taming that problem is something I wrote up in a few papers on the what I call the quantum equivalence principle. So the idea of the quantum equivalence principle is that even if you have indefinite causal structure, you can still find a quantum coordinate system. So this is a quantum coordinate system. It's like a quantum reference frame. It's a sort of so you can have a quantum coordinate system in which the causal structure is definite locally. Okay, so this is analogous to the usual equivalence principle, where you can find a classical coordinate system where the reference frame is locally inertial. The idea is that you can find a quantum coordinate system where you have locally definite causal structure, and in that case you now get the usual the usual light cone at that point, and in the vicinity of that point where you have a future and a past defined. And so it's in that particular context where I wanted to understand time symmetry, because that would be exactly the place to apply it, when you have local definite causal structure, because you're in a particular quantum reference frame. So that's the way I see forward on that. And I've written papers on the subject of this quantum equivalence principle, but they're sort of in a different language. They're not in the operational language, and so I want to bring those two things together. So that's so it's a very interesting question, and that's kind of that's the way in my own research that I see this going.
Thanks.
Dingja, do you want to ask your question?
Yes.
Hey,
so my question is directly related to Robert's. I think. Do you hear the noise? I guess.
It's fine. I can
hear. Okay.
Yeah.
Right. Okay. So. So it seems many people in quantum foundations are interested in building frameworks instead of building models. So I'm thinking about your perspective from somebody that works on quantum gravity. So to many of us, it seems we have a good enough framework, which is Robert's framework, to do quantum gravity. In the sense of having a general framework of quantum theory, to many of us, we do have it already. And the question is model building. How do we describe gravity? Which variables do we use? Which kind of precise, action do we use? Which kind of precise path integral formula do we use? To many of us, it's like more of a technical question, and there's no question left at the framework level and conceptual level. So I wonder, from your perspective of a framework builder, do you see anything still unsatisfactory with these frameworks we have? Do you see something that we can improve in the frameworks?
Yeah, so trying to think how to answer that question. So I certainly agree with the general thrust of your question, which is that to make progress, we ultimately have to get busy and start putting real physics in, and so we can do calculations and calculate numbers that we can measure in real experiments. And if you're just building a framework, you're kind of missing that. And definitely, I like the framework that Robert has. I've been sort of building in parallel, like the causal load framework and various operational frameworks. There's some parallel development of ideas between what Robert has been doing, starting with his general boundary formulation, and more recent work where he goes into objects that are linear in probability, his positive formulation, and my own sort of development, which has been linear in probability, and so on. And there are different ideas in those different frameworks that we could get into if we had a couple of hours. I think we're not. I mean, we've had a lot of these basic ideas in quantum gravity for a long time, and we're not quite there yet. So, bringing conceptual ideas in from quantum foundations, I'm hoping it will be very useful. I mean, that remains to be seen. It's kind of a new approach, but since there are, something like 1,000 string theorists and 100 people doing loop quantum gravity and so on, like I think exploring different ideas is always going to be useful, because otherwise you keep doing the same thing. So so I think I don't think the conceptual work is done yet. I think we need to bring ideas in. We need to understand, well, things like time symmetry really need to be understood properly, and perhaps that way we can make progress. But the general thrust of your question, I completely agree with. You have to, in the end, success is measured in terms of actually being able to do real calculations, and and we're not there yet.
Okay, so next is Marko Vocinovic.
Are you sure that I'm next? I think that other people have raised their hands before me.
Onyan, maybe, but between you two, Onyan or Marko, I don't know who was first, actually.
I guess Onyan was first.
Ah.
Okay, I can go. Okay, thanks, Lucien. That was very provoking, I would say. So again, as you know, you mentioned this work of ours, and it's a competing approach, if I have to define it somehow. So I have the following question, basically, just to properly grasp what you're doing. What happens to this? So in some sense, as I understand it, what you did is that you defined a specific class of operations which respect a certain property, say unital operations or something like that, which are time symmetric in a particular sense. What happens to the standard, let's say the time asymmetric operations that you considered in your previous works? What is the attitude towards them now?
Okay, so they still appear, but they're you can generate them just by sending specific specific incomes into the operation, and then conditioning on seeing that particular income. So it's still there. If you think about the diagrams I drew building them, then you can see that with that you can construct. It's just a change of attitude. Although you can build them, there's this notion that those incomes should really be thought of something that you might want to put a probability distribution over, and you should consider them, as part of a set. So they're still there. It's similar to the situation, with the work of Aharonov, Bergman, and Leibowitz, where they show how to think about quantum theory in a symmetric way, but it's the same theory. They haven't changed the theory. It's exactly the same framework. It's just that you can present the results in a symmetric way.
Right, but in a sense, if you, if you want to think consistently about operations, like you have an apparatus, maybe you do something, but you can embed it in a larger system and so forth. Almost all operations that are of practical interest are somehow effective. They arise from conditioning on selecting some system to be in some state, such that effectively some other system undergoes a specific transformation. We're not taking the full quantum field theory and saying everything evolves unitarily and that's the end of the story. Here in this operational perspective, we're really looking at kind of effective scenarios that can arise within the universe, and we're stating certain rules about them. And for all of these, as I understand, in all these circuits that you draw, these operations, they arise effectively in that sense, for most of them. Practically, what you do in the lab would arise by setting up the state of some system or some ancilla in a specific way, for example. Normally, in the standard approach, which is time asymmetric, we do that in the past. But we will do it also even for the unitaries, the effective unitaries that you would create to act on a specific system. Because you need to, if you look from a larger perspective, maybe the spin was interacting with the magnet, but you set up the magnet in a specific state such that actually effectively now it's going to start precessing in, along a specific direction. So it's, if they're all effective and arising in such a way, then it seems to me that here, out of all the possibilities that we can realize, we are declaring that we should be just interested in a certain subclass of those that can naturally arise. We should be only interested in a subclass which has a certain time symmetric property, right? The one you described.
No, because it's not. The class they give you is the full class. Like it's all the operations can be written in this form. It's just that we're trying to keep our perspective on them. I'm glad to see again Carlo nodding his head. It's good. We're keeping our perspective on them time symmetric, but it's the full class of operations that's there. You know, quantum theory has these properties I gave you. It's just we don't normally focus very much on these things I call incomes. So it's not different. It's the same, and it's a bit more general. This you know, again, you see it in the DiBaggio et al. Paper. It's a bit more general because we don't normally think about the time reverse where we post-select on an ancilla, or we pre and post-select on ancillas. So actually, there's a slightly more general set of operations that appear in this time symmetric framework that aren't normally considered. Yeah, although it's also the case that we can. It's also the case that we can use just the usual approach to get all of this physics. It's not there's not new physics. It's just a different way of looking at the physics.
Okay, that's probably something that I have to still think to understand correctly. Just a question about like when you say, for example, I can prepare a specific state, and I can know that I prepared a specific state to put into one of these operations. Was it I don't know if it's an input or a setting. The preparation of a state, how is that? Is the theory that you described, is it supposed to be, does it exclude, is the preparation of a state going outside of the theory? That's my question.
Okay, good question. Yeah, so so the answer is no. But it is an interesting question. So the preparation of a state sort of looks like this, and you have an income coming in, and you choose that from a set of a maximal set, and then you prepare the corresponding basis state or the corresponding maximal state. So I mean, this object is consistent. You can, yeah, I mean, yeah, I'm not finding a very good way to answer your question. I mean, this object is consistent within the theory, and it is modeled.
But this wire which comes from the side, is it not supposed to be possible to see as a system also?
I mean, one way to think of this is the wire that comes from the side. There's a promise that you're going to look at it in a particular basis. Okay, you could think of it like that. You could think, in the case of quantum theory, you could think that it's a quantum system, but there's a promise that you're only going to look at it in a particular basis. If you take that point of view, then this box, all it's really doing is twisting the wire, you know, like so. So I didn't draw that very well. Let me try again. Yeah. So if you take that point of view, when you put this kink in the wire, there's a promise that you'll only measure it in a certain basis in some sense. Yeah. But I think everything is internally consistent in this sense. It's fine. just while you're thinking, I had a question for you as well. Your paper with Nicholas Surf, in that paper, it's still standard quantum theory, but you're finding a different way to present it. Is that right, or are you modifying quantum theory?
Well, it depends what we call quantum theory. There is a lot of here we need to a lot of definitions, but let's say it is. In summary, there it's if I can just very formally say what is the difference I see here is that here what is considered operations is reduced from the, that is my understanding, but you said that actually it's enlarged, the standard definition of an operation.
Yeah, I would say it's enlarged.
But okay, my feeling is that you were considering unital operations only. Maybe I just didn't get the point. And unital operations are a subclass of even the one way, the asymmetric class, whereas what we do there is we define operations to be definable by both pre and post selection, because it's, as I said, we normally condition on some variable. So the way we view it is just, you can again say I have a box, I have an input and output system, and around it a bunch of classical variables, but I allow any to take any of them and interpret as systems if I wish, or to condition on whatever I want to call a setting, etc. So it's, I think it's a bit more expressive in that sense, but the conclusions are that actually by arriving to a rule which is more general than the standard linear rule, the Born rule, a priori this theory permits other things that we do not necessarily observe, such as we could live in a universe in which, let's say, we are able without post-selection to realize in practice some operations that are not of the trace-preserving kind. Something that looks like post-selected operations, those are the kinds of things that we could do with post-selection in our world, but a priori they could be doable without post-selection. So the theory is formulated in such a way that a priori that allows more general things that we normally consider.
Okay.
And it's natural within that theory that Born's rule is not a fundamental one, because it simply applies to a specific subclass of possibilities. Yes, so it's like for very special circumstances, yes, the Born rule holds, but you might as well, there are more general circumstances allowed by the theory, therefore we just regard it as a special case, this rule. And so it's a more general theory, I would say, compared to the asymmetric one, okay? And now I still have to understand what you talked about to be sure that I properly interpreted it. Yeah.
Okay. I mean,
just if I may just use the opportunity that we're talking just to ask another question, maybe this can also help me clarify my understanding. Now, this theory, I suppose you would propose it as a fundamental theory, one that should in principle be able to account for all experience, physical experience, excluding gravity for the moment. We just forget that it exists, and we take that there is a notion of time, and then I suppose that you would think that this is a fundamental theory that should in principle be able to describe everything. If so, is it compatible with, how does it give, how can you account for the fact that we can, in fact, signal to the future?
Oh, so in this approach, typically, you know, so the theory is that you can't signal to the future without knowledge of the past. So you can't send a signal about M into the future without some knowledge about the incoming. If you have a flat distribution over the incomes, then you can pick up no information about M. But if you have some knowledge, so if the distribution about M over the incomes is non-flat, which is normally the situation we consider, then you can signal to the future. And I think like this appears, you know, again, I think in the work of Di Baggio and also Carlo's, things like this sort of thing. You know, it's because we tend to carry these memories of the past with us. But there is an interesting situation. So here's one question is, and this is something I've puzzled over. So in the von Neumann model of measurement, you assume an initial pointer state, and then you read off the result of the measurement from the change in that pointer state. Now, the only problem with that point of view is that you sort of need to know, you need to remember what the initial pointer state is. But hey, no problem. You could just introduce another measurement apparatus to measure that pointer state, and then you could read off the pointer, like where the pointer state is from that measurement. But then you get this infinite regress.
Exactly. Yes.
And so there is an issue there, and maybe other people can have a comment on how to resolve that.
Precisely the issue that I was asking about, yes. So, and I think that essentially, I don't know. Yes, I'll be interested to hear what other people have to say about that. Really.
Yeah.
Because I think that you need to break the symmetry. Yeah. With unital operations, I have the feeling that you cannot resolve this. So I think that is one crucial reason why I would prefer the other approach.
Okay, please, Andrew.
Yeah. May I jump in? Since I think part of this is it's like the question of signaling and the question of preparing a system are basically the same question, because if I want to signal to you a 1 bit, say, instead of 0, I need to prepare the 1 bit deterministically to send it to you. Because if I cannot choose what I'm going to send to you, then I'm not signaling really. There's a connection, but I'm not influencing the physics in your lab, right? And I think, yes, so you need to break the symmetry in some way, but it doesn't mean that the underlying process is not a unital process. As in, one way to see it is that if I get a qubit which is in a state that I don't know what state it is, I just measure it, and then I get either 0 or 1. And after I measure, I can decide to send it to you. So if I get 0 and it's not what I want to send you, then I measure it again. I measure another qubit that I don't know where it is, and I send you that. Right. So I'm still doing all of it with the unital operations, but there's this, if you want, it is post-selection. So it's like unitals plus post-selection makes it work.
But okay, this still is kind of, isn't it moving the pre-selection to a post-selection again? It's breaking the.
Yeah, I guess it's like you start with the unital, so the stochastics, or these double causal things, but you add a layer where you allow for post-selection or pre-selection. I don't think that makes much of a difference, and that's what breaks the symmetry. But
I'm not even sure that if everything starts with a maximally mixed state, I have the feeling that there is no way to actually prepare anything, because if everything really, like your apparatus as well as the system, is maximally mixed, they evolve unitarily, they stay maximally mixed, and you need to have correlation between some memory and the system you're sending.
Yeah, I agree. But the thing is, the universe did not start in a totally mixed state. It started in a very low entropy state.
Right.
So we have unital local laws plus like a special boundary condition in the past, which selects the direction, like this specific direction. But there's nothing, I mean, it's kind of fundamental because it's the beginning of the universe, but you could see it all the other way around, and you say there's a special state in the future, and everything is evolving in the other way.
Right. So that perspective therefore answers my previous question about whether the state is external to the theory as positively, at least. I'm not sure that whether Lucien shares this, but my understanding is that here you say, well, the dynamics, I can always take it to these unital operations, maybe even just unitaries, but you can introduce all these outcomes if you like. Mm-hmm. Nevertheless, you restrict yourself to unital ones. We can mimic every operation via unital ones with suitable pre-selection or post-selection, but then the actual initial states, we take it to be an external to the theory. Is that something that Lucien you would agree with? Is that the perspective you take, or you would think that?
Yeah, I mean, my point of view is still evolving, so I'm not sure I want to. I mean, certainly I'm worried about assuming there's flat distributions coming in. So I mean, the statement of causality, as I stated it, is if you have a flat distribution, then you can't read off any information. So that I think is fine. But you know, whether one should assume a flat distribution if you have ignorance over the past, for example, then it seems to me to be dubious. So it would be, and this is kind of the point of this generalized framework I was aiming at the end, where you don't have to do that, and perhaps you can think in a more general sense, and it might be a general framework like that is more suited to the actual universe we live in. Yeah.
Yep. I would suggest that we move on the next questions. There are still 3 people who would like to ask questions, and since time is passing quite fast, then
in the forward direction.
There's Marco, then Carlo, and then Philippe. So.
Okay, so I'll try to be short. My question is related to a statement that you made at the end of the lecture, or near the end of the lecture. It is about some relationship or some kind of connection that I didn't really understand between the flatness of the probability distributions on one hand and the flatness of space-time geometry on the other hand. So if I understood correctly, you made some kind of identification or connection between the two. Can you explain that? What do you mean by why would these two concepts have anything in common?
Okay, so it wasn't meant to be a formal connection. I mean, perhaps there would be such a thing, but just as an analogy, and the analogy would only hold if I can find a way to deviate from the flat case in the probability. So in special relativity, general relativity, the inertial systems play a special role, and they're a kind of preferred special way of looking at a system. But you can look at a system from a different point of view, and then in the case of quantum theory, having these flat distributions coming in and going out seem to play a special role. They make the physics very simple, time symmetric. But there may be reasons you want to look at the physics from the point of view of having distributions going in and going out, which are not flat. And so then you'd want to find a way to go to I call the distribution going in and going out a conditional frame of reference. I may change that name, but that's the name I have at the moment, because it's that kind of the conditions outside of the main part of your experiment. So if you can set up some mathematical machinery for transforming from one conditional frame of reference to another, perhaps you can get some mathematical traction on this idea. So that's roughly the idea. But it's still preliminary. I haven't really got this working yet, yeah, it's not entirely clear it's even the right thing to do, but it's something I want to think about.
Okay, thank you.
Carlo?
Thank you. First of all, thank you, Lucien. This was extremely nice. I liked everything you say. I found it extremely clarifying. And I mean, obviously, I agree with everything you say. And but also, I want to stress that I was very confused at the beginning of this period of working on these things. And perhaps you remember, Lucien, you and I also had some discussion about that. And
yeah, absolutely.
I was confused by what you were saying. You were confused by what I was saying. And I talked with you. I talked with Bob Cook. I talked with many people in the quantum information community. And it was really Andrea who somehow was able to disentangle a lot of these things. And I have progressed a lot in my understanding, and I feel that there is much clarity today. And in fact, I would say that from this perspective, of course, all open questions like the one Robert is posing, but I find this kind of things that you do extremely clarifying. Now, at the end, especially trying to answer Ongyan, you expressed some questions about the idea of a flat distribution to start with, and the relation with the obvious known-time symmetry of our experience in the lab, which is undeniable. And I just want to make one small observation about that, which is there's a question about the non-time reversal features of the world, which has nothing to do with quantum mechanics, right? It was there before 1925. In fact, before 1900, before Planck and Einstein and Bohr and everybody, there was a completely analogous problem, which is that we have an experience of a macroscopic world which is time oriented in every single phenomena, right? Things fall and stop, and I can decide of the future. I cannot decide about the past. I remember the past and I don't remember the future. And there were classical mechanics and fundamental laws, including electromagnetism, which were time reversal invariant. So the question was open there. I think that all this discussion about time reversal symmetry of quantum mechanics should not be confused with the previous discussion. Namely, the question here is that, has it changed something with the discovery of quantum mechanics with respect to time reversal symmetry? That's the actual question. And the answer on which I see convergence is that the answer is no. Which means that, of course, there is still a question about why do we remember the past and not the future? Why can we decide about how to run an experiment in the lab tomorrow, but we cannot describe how we cannot decide how to run an experiment in the lab that we have already run it. This is a different set of questions, and as Andrea, I think, was hinting a moment ago, we have a lot of information about that. I mean, we know why we remember, to some extent, why we remember the past and not the future, why we can decide the future, not the past, why things happen in one direction and not the other. We know why I see the pen falling and stops and that I don't see the opposite. So there's a huge amount of phenomena, including the actual what happened physically. When I go in the lab and I decide on an initial state, I prepare a state, right, which are obviously non-reversible. I cannot undecide, okay? Like this pencil cannot jump up by itself. So there's a lot of irreversibility in the world for which we have a large amount of understanding, perhaps with some open gaps, which I don't want to enter it, but is an understanding which is based on the fact that we use macroscopic variables. So there is the statistical mechanics, and there is past law entropy, which is a contingent fact of the world. This is what Andrea was saying. It is a contingent fact of the world that the universe was strange in the past, was low entropy in the past. The sun is an irreversible phenomenon, and we're immersed in an entropy gradient, which colors enormously the kind of phenomena that we observe. Namely, out of all possible dynamical phenomena, there are only macroscopically those which happen in one direction, not in the opposite direction, which explains completely, it seems to me, up to the open questions about thermodynamics and past law entropy, which are those open questions, explain completely the irreversibility of our experience in laboratory. So the answer to Ongyan, when he says, well, Lucien, you're looking to a subset of time reversible phenomena, I think it's exactly the other way around, is what Lucien was answering. Dynamics allows a much larger kind of phenomena, and this set of phenomena are time reversible, okay? The ones which are actually realized in other world, described macroscopically, are irreversible. So I don't think there is anything mysterious here anymore. I mean, there are open questions like, how can we formulate this more generally, and so on and so forth, or how to understand this this better. And there are open questions: why was the universe started in low entropy? We don't know that. And there are open questions like what Lee was saying. Well, perhaps there is some fundamental time irreversibility that sort of motivate this low entropy starting. But the phenomenology that we observe is accounted for entirely, I would say, seems to me, by a time reversible, by quantum dynamics that can be formulated in a time reversible manner, in the classical limit by a classical dynamic, but can be formulated in time reversible manner, plus our understanding of what happened when we coarse grain and we go to macroscopic variable, plus a contingent factor of the world, which still confuses us a little bit, that the entropy was low in the past, and therefore we remember the past, therefore we have the sense of freedom of the future, and so on and so forth.
Yeah, okay, so I agree. I think I agree with everything you said, except I want to, there's a few points where I'm worried about it. So we don't, so this picture of, some initial state with low entropy that evolves and therefore, is able to account for the irreversibility we actually see, is all correct in the standard theories. But there's a concern I have is that when we go to a theory of quantum gravity, we may no longer have this idea of fundamental time, evolving forward. There may not be a global way to assign, a t parameter and evolving forward. And so even if effectively that might work, fundamentally there's a deep problem there. And so we have to look to ways to sort of contend with that battle. And so my perspective is to try to get operational grip on as much as we can, because operational ideas have the property that you can take them from one fundamental theory to another. If the fundamental theory physics changes, maybe the operational ideas can be transferred. That's something that was done in the past in say the development of general relativity. Operational ideas like the equivalence principle was actually true already in Newtonian physics, but it was ported over to a different physical theory, whilst changing the background physics tremendously. So I'm really worried about this sort of account of irreversibility that relies on starting in a low entropy state if we have to get rid of the notion of time as a fundamental thing. So that's on the one side. On the other side, I wonder if there's some work that we can do still within this kind of framework. So, and we can think about porting classical information around. So I wonder if I should draw a diagram. So here's, I'm just going to draw so I drew this kind of diagram, before many times, but you may want to do something where you actually copy. So you make this R, it actually produces two copies that are in the same, can you see that? So there are two copies now in the same state, these are classical, so there are two copies in the same classical state, and they evolve forwards. And now you can take this information forwards over here, and it looks like you can start to compare. Sorry, I hope you can see that.
Yep.
You can now compare, and this will be a way to try and bring information forwards. And now, if you take this R box also to satisfy local flatness, then X, these two copies of X have to be a flat distribution over there. So there's some extra mathematical machinery you can bring into this. And so, so what I'm hoping is that it's possible to build up a sort of mathematical framework that's still in this kind of circuit language that talks about porting information around. Because if you want to actually measure joint probabilities, you need to have local access to both of the things you're trying to measure. So I haven't set that machinery up yet, but I think it might be instructive. And while it won't answer the bigger question as to why there's time asymmetry, it may help us get a grip on some of the technical issues. Yeah, so I like your question. Those are the two responses I have immediately. And also incidentally, I really enjoyed the conversations we had back in starting in May, and it certainly influenced my thinking on the subject as well. I feel like I'm playing catch up to some extent. I'm still not able to think fully in a time symmetric fashion, nor say the alphabet backwards. But I feel like you guys are a bit ahead of me in the game.
Thank you.
So Philippe, do you want to ask a question?
So yeah, thanks for the talk. It was really interesting. So what my question has to do with like the discussion with Carlo, and I think I'm confused by the same things as Ongyan was. So like I understand that you can have a fundamental physical description that is time symmetric, and then you have observed data that is time asymmetric, and it doesn't contradict, like it doesn't falsify the fundamental theory. But the way that I understand operationalism, it seems that if you have observed data that is time asymmetric, then it would falsify the operational theory that is time symmetric. That's like very naive, but so at the operational level, if data is what we're talking about and like joint probabilities of things we call input and output, it seems that we do actually observe things that don't satisfy double flatness. So I was wondering, how should I think of this?
So actually, the diagram I just drew, and it's developing a theory of porting information around, is sort of one way to try and address that. Maybe I could just draw the time symmetric diagram. You can also look at, you can consider joint probabilities in the past before you do an experiment, but those are kind of conditioned on, sorry, here, this diagram at the bottom, those are conditioned on some promise in the future. So I think the answer to the kind of question you're asking is going to come up in studying how you get information to the same place, so you can actually measure the joint probability that you're interested in. You know, like in real experiments, they have to send wires to some coincidence counter. So there's actually a real operational counterpart to this question in experiments. Yeah, so I think that's the answer to your question will lie in that direction, but I don't have an answer beyond that. I think there's some mathematical machinery that should be developed.
So is it like committing yourself to a certain redescription of like operational situations? Like if I have an actual box that has inputs and outputs, and the outputs don't have a uniform distribution, for example, we just say, okay, I choose to redescribe it in a way that you can see that it somehow arises from a time symmetric description. But now what I'm wondering is, like, is this really a operational description, or just some, a fundamental description? And are we losing the strengths that the operational approaches have by sort of mixing in ontology and operationalism together?
Yeah, so now I'm not sure I understand your question. Can you ask it again? I'm sorry.
Well, so it's kind of clear that in practice you can build machines that have things that we call inputs, things we call outputs, and then you run it a long time, many times, and then you reconstruct the joint probability distribution over the inputs and the outputs. And the marginal of, say, the outputs is not uniform, even though the marginal of the inputs is, right? Yeah. And then, so that's kind of, okay, at this, what I consider maybe naively to be the operational level, the double flatness assumption is violated. But then we say, okay, we could actually redescribe it in a way that maybe involves some post-selection or whatever, such that at the fundamental level, which is, in my understanding, no longer operational, we do have the double flatness property.
So hold on. So the double flatness property is a statement. If you send a flat distribution in, you get a flat distribution out. It's not saying that you have to send a flat distribution in.
Yeah, what I'm saying is it can be the case that there's a flat distribution of inputs and non-flat distribution of outputs in practice, right? Just the process that takes a random bit and resets it to 0.
So I'm saying that every time you do that, every time you have something that does that, really you've secretly ignored some incomes, and you didn't actually start out with a flat distribution. So a lot of the ways of thinking we have in quantum information, for example, but really resetting, if you break down what's happening inside a reset box, there's an income. I think this relates to something Andrea was saying just a short while ago. There's really an income that you are ignoring, and you have to be careful to find all the incomes in order to do that. So yeah, so I think there's so if we're going to think in a time symmetric fashion, there needs to be a process of sort of almost re-educating ourselves in terms of the standard tools of quantum information, because often they assume a very time asymmetric way of thinking, and they gloss over there's things that we'd have to take into account if we want to think in a time symmetric fashion. I mean, we don't need to think in a time symmetric fashion, but if we want to.
Okay. But I don't want to take too much time, but this is, yeah, it's committing ourselves to a sort of hidden variable model, not in the sense of local hidden variable model, but a description in terms of things that have a property that is not observed.
Yeah, that's
what is operational about this.
Okay, so
that's what is confusing to me.
Yeah, so when I defined double flatness, I did talk about it being with respect to a maximal set, and it might be you don't actually have access to the maximal set operationally, in which case the double flatness property doesn't, in which case you're not able to see if you've got a flat distribution coming in. So yeah, so the hidden properties you're referring to are this maximal set. And you need to have access to all of the elements in the maximal set to be able to invoke the double flatness property.
Okay, this clarifies. Thanks.
I think, Onyan, you have another question. You want to say something?
If it's possible, I can. Yes, I don't know how much time we have, or what is the.
Now there is. No one else is on the waiting list for questions.
I would like to ask one question, but I cannot raise hand because I'm hosting, but I will do it after Onyan.
Okay. Then the time we have depends on the patience of Lucien. So he is fixing the bound.
So I didn't understand. Shall I go now, or Marius, would you like to, if you've been raising a hand for a while?
I can ask after yours.
Okay, so first I would like to comment, and then I'll come back to a question.
Sorry, I'm having some problems with the internet.
Do you hear me?
Okay. Okay, good. Yeah, now I think the internet caught up with you. Okay, good.
Try again. So basically, first I just want to respond briefly to Carlo to say I'm not suggesting that there is any mystery in that. Specific mystery here. I think I have rather clear understanding both of your point of view, and also I should say the same is discussed with a slight difference in our paper about in terms of boundary conditions we can account for this asymmetry and so forth. But there is a difference in the approach, in the attitude, which has to do with how we define the rules of the theory. And I want to and this has to do a little bit with my subsequent questions to Lucien. So as I said, in our approach, we do not restrict ourselves to just time symmetric operations. Of course, we know that in practice, we can realize those time symmetric operations even forward in time. And that is why I said that I think that here it's a restriction, because all of these operations that you described can be done without post-selection in the usual way, just by the same methods that we use to realize all these quantum channels that don't preserve the symmetry property you described. In just the same way, we could also realize this in practice. And in that sense, I think that we're talking about a subset of all allowed operations. Now, this theory here postulates that they are the operations we should consider. And hence, quantum theory is symmetric in the sense that it is built up of these types of operations and they respect a specific rule, which is this linear Born rule. Now, from a practical perspective, of course, I see this as restricting ourselves to particular types of operations, which in practice we would realize by just preparing flat ensembles from the past. If I'm to describe how I would do those in the lab, I would do it this way. But in the lab, I can also do other things. And now we are saying, you know what, I should not consider those other things. I should not define my theory to be about those. Because if you do that, if you want time symmetry, then you have to actually allow post-selected operations, and then a more general rule arises, which is then, as Robert mentioned, I think one of its advantages is that also naturally extends to a time agnostic, time neutral framework, and we have done also that, explaining this relation to Robert's approach. However, let's say now as I understand in this proposal here is that these are the fundamental or the types of operations we should think about in our theory. There are these bistochastic or relaxed bistochastic operations or whatever is their analog in the quantum. Now, that's fine, but now I would like to ask, how is that defined in practice? As I understand operational probabilistic theories and this whole operational approach, you have a concept about something which is defined solely in terms of laboratory procedures to start with. Mm-hmm. And then using those laboratory procedures, well, there are some assumptions such as the circuit. The circuit is a very important assumption actually. But modulo this, once these assumptions are given, we can find out the theory. We can find out what the theory actually is in practice. Here, it seems that, at least the way I think about how one would realize these time symmetric operations in practice and how one would realize these other, which are not time symmetric, they seem to be realizable via the same methods, fundamental methods. And it seems to me that now, through some ad hoc principle, we say we are not going to regard those which seem time asymmetric as equally fundamental in our theory. They will be like derived, like the outcomes of operations that people normally think when they adopt the time asymmetric approach. Mm-hmm. But it appears to me that the way I would do them in practice is by, again, selecting a specific variable, and now it seems that you're saying, yeah, you should select the variable in such a way that you prepare a flat ensemble. This seems very ad hoc in this direction of time. In the opposite, I can understand people who believe the quantum theory is time asymmetric because those arise naturally. They arise without post-selection. If you restrict yourself to procedures that don't involve post-selection, it turns out that we only can do those kind of some restricted class of operations you can mathematically conceive. And then I can understand that people would think this is a fundamental principle and so forth. However, I believe in time symmetry. I think it is elegant and I would like to have it in my theory. Therefore, I see that what is a logical way to do is to actually permit the kinds of things we see back in time to be allowed also forward in time. Therefore, in principle, kind of symmetrized by enlarging the group of what we normally call operations, allowing even the post-selected ones to be called valid operations, rather than restricting it and saying, oh, just the unital ones should be considered. So I was wondering, when you think about those being the building blocks of the theory, and maybe the initial state is somehow external, even if you want that theory to hold at the lower effective level inside the space-time in which we live, not just some statement about the full universe, but really like we want them to hold at any level for any experiment, then how shall we think that these are the true ones or the good ones, and how do we exclude the bad ones? That's my question.
So I mean, I think the whether one which is whether something is a restriction or not is a tricky question, and it kind of depends a bit on perspective. I think there's a perspective whereby the operations I've described are not a restriction; they're actually the full set of operations. The reason they have the unital property is because you define that unital property with respect to a flat distribution over all the incomes, whereas in the normal approach, you would make some of the incomes have specific values. So that you take the ancilla, for example, to have a particular value going in, and then you lose the unital property. Whereas the way I define what you're calling the unital property, I'm calling it this relaxed bistochastic property, is with respect to all of the incomes and also all of the outcomes. So I think I don't really think that it's a restriction if you think about it in those terms. It's just a matter of perspective and how you define these things. So I think that was the main thing I wanted to say in response to your question, but you said something else as well, and now I don't remember.
It was the tension I see is that if you think about these things not as being out there, like maybe you take some very isolated region of space-time, then I can maybe see that in a certain sense, okay, this is a unitary operation there because it's like really maybe a closed system in some absolute sense. Like take a suitable region of space-time with a suitable shape. But for all the others that we do in the lab, even those that you do like a unitary on a specific subsystem in your laboratory, you are selecting you're setting up some subsystem of your larger laboratory in a certain way, such as to get it. And
that's all fine. Yeah, that's all fine. I mean, you can do that. It's just the properties that I give you are defined with respect to, distributions over all the things all these incomes. So I don't think that there's really a restriction. I think that it's the same. Now, one thing I do agree with you is that it's rather odd to single out the flat distribution as if it was special, and that's why I want to develop this more general framework I talked about. So to assume, if you have, for example, if you have an open income and you're ignorant about what goes into it, to assume that it's a flat distribution, I think is dangerous. One shouldn't make that assumption in general. Ignoring the past, who knows what's coming in? If you ignore the past, anything could be coming in. So I agree that there's a problem there, but nevertheless, mathematically, all the properties I gave you were defined carefully, and I think that they hold. And I think that any operation can be understood in these terms. It's not a restriction.
Just a thing. So am I understanding correctly that in a sense what you're discussing, two of you, is just when I'm in a lab and I want to prepare something with spin up in the Z direction. So one way of thinking is that, okay, I'm capable of producing a state spin up, and so my input is as a state spin. And another way of thinking is that I start from, let me make a cartoon here. I start from in spin space of a flat distribution where I don't know anything. I can always think about that. And I add a procedure which is accounted by in my formalism, which is what filters out what I want, which is in a sense also what happened in the laboratory, because in the laboratory when you prepare something, essentially you're filtering out. So am I correct here in saying that nobody questioned the actual thing that can be done in a lab? Lucien is saying I can describe those things within my formalism. I'm not assuming that in the lab I cannot do the kind of, starting from a spin-up state that I usually do. Is that the bottom line?
Yeah, that I agree with what you just said. Yeah, I'm not sure if Onion does.
I'm not sure. I have a feeling maybe there's some misunderstanding here, because I have the feeling that my question is not being addressed, but it's possible that I am using language that doesn't fit to exactly that language you use. So if I do to try again, so it's not like you said the full universe or the full quantum field theory evolves unitarily, and then on top of that I have some initial state. That's not the theory, as I understand it, that you presented, because that theory is just about that, what I said. Rather, I see the theory as a statement about the types of possibilities that can arise, different circuits that we can have, and the types of properties that the fundamental or basic operations that build out these circuits have. So my natural question is, what are these circuits supposed to be in practice? So for what is this theory that you talked about supposed to hold? Not for the full universe, maybe I can accept that. But if we go down to some effective situation, then how was that defined? If the whole point is to describe it by enlarging everything to the full universe, and if that's the whole point, then I have the feeling that there is a different philosophy here. It's something.
Okay, yeah, no, that, I mean, that wasn't it. I'm not trying to enlarge it to the whole universe, and certainly I'm not dealing with quantum field theory. I'm dealing with sort of, finite dimensional Hilbert space version of quantum theory that's used in quantum information. Yeah, and I think quantum field theory, or any theory where you have a continuous rather than just a discrete set of basis states would raise questions here, because then you'd need a measure with respect to which you define this flatness. But no, the ambition is restricted. It's to take the standard formulation of finite dimensional quantum theory that's used in quantum information theory, for example, and make it time symmetric. One can try and draw lessons from that for the bigger project that you're describing, but that's beyond the ambition of the current project.
Can I ask a question too, again, because I want to unpack what he's saying. Maybe I'm not sure I understand it. There is a simple-minded version of the claim here. The claim here is that everything quantum mechanics predicts can be expressed in the form, there's a probability distribution given a probability distribution on B, and those probability distribution are time symmetric. So they don't know which one come first and which one come later. Now, this is one way of putting the claim. Perhaps it's a little bit oversimplified way of putting the claim. And then the question is how to actually implement that. Again, are you saying, I think this claim is wrong? Or are you saying, I have a better way than the one of Lucien and a better way to implement this claim? Which one of the two, or a third?
Probably something like the second, but it might be a third. So let me say that. Of course, we know that, let's say, when you say the rules of prediction for probabilities for A given B, those that are given by the Born rule, of course, on the one hand, let me just remind people, of course, it holds for pre-selected operations in practice. And this is maybe coincidental. This is the approach we take in our paper. We ultimately explain it as coincidental. Just happens to be a very special boundary condition, etc. Okay, but the same rule now, in your paper, you say it holds also back in time for retrodiction or postdiction, okay? This, of course, is true, provided that we talk about all those experiments in which the initial state in the normal direction is prepared in this flap distribution, or maximally mixed state, okay? So this, I think, is correct. This is obviously correct. It's been actually discussed many times by many people, even already, maybe even in Watanabe's paper, which precedes ABL. That is, of course, correct. The question is, do we take that rule to be the rule of our theory, or shall we actually think that there is a better way of doing it? I think because this rule, by definition, only applies in a restricted setup, it seems to me natural to say that, well, it doesn't quite sound like the rule of our theory, like a good rule for a theory, because it really, by definition, applies in a restricted setup, because the theory in principle permits all kinds of other things to be realized. It permits in principle to have initial state, which is not the maximally mixed and so forth. So why not formulate a rule which actually is capable of dealing with all these other things that actually we even see to be realized? So that is, so our proposal is to do that instead of, I again say restrict, but to me, it's a restriction to restrict yourself to the flat distribution. Sure.
So you're saying, in the standard sort of time orientation, I make no assumption about the outcome. I make some assumption about the income. And you're saying, I get asymmetry if you do the opposite. And you're saying, well, you only have a formalism for allowing arbitrary assumption about the income and the input state and the output state, while you're reading Lucien of sort of looking only a specific case when you have a flat distribution on the coming in. And I think Lucien is answering, no, but that's a formal part of the theory. If you look at the theory more carefully, you see that it includes all the predictions that you can write by putting an initial state and a final state, essentially, appropriately. So it seems to me more of a technical. What's the best way to formulate it? The end point, as far as what time reversal symmetry is in quantum mechanics in a operational approach, is very similar. It's more of a technical dispute of what's the best way of doing it.
Right. However,
so one thing to say. So I think this sort of generalized theory of conditional frames is something that one should think about, because it addresses, maybe one can think about different distributions coming in and out. And I had a suspicion that I think that theory there may be some non-linearity as you transform between these different frames, because you need to divide by denominators that normalize your probabilities. And as I was reading your paper, Onion, I had a sense that there may be a connection at that stage between the different approaches. I wondered if there was something there that could be done. But when I read your paper, I didn't have a full understanding of the sort of conceptual, the conceptual ideas in the background. But because there's something nonlinear in your framework, isn't there? And it felt to me like it might be the same kind of nonlinearity that you would get in this conditionalizing process. So I do wonder if there's a way these different approaches can meet in the middle eventually. I think there's still something to be understood.
Just to maybe just to comment on, yes, it seems like a technicality. I agree with Carlo about that, but I think that if one continues thinking about it, actually, it can have some implications about the kinds of things you consider allowed in your theory. Because if you say, okay, my theory is just in terms of these time symmetric operations, and then I should also, of course, allow some initial or boundary state to be put here and there, and I know how to calculate probabilities out of that. But my main probabilistic rule is the linear one. Then, if this is the main rule of your theory, for instance, when you start asking questions such as how do I describe, for example, symmetries, what kind of operations are allowed, how can a closed system evolve, and so forth, you would make some conclusions. Whereas if you adopt the other perspective, more general things are in principle possible. They may not be realized in the world, but this I see as more of a circumstantial question, like which Hamiltonian drives our universe, or which boundary conditions happens to be in our universe. But a priori, more general possibilities are allowed by the formulation I talk about. And I have the feeling that this is interesting because it might turn out to be relevant in some regimes. And already Robert pointed out, I think this is one example where I find very suggestive that this might be a fruitful approach, is that already if you start considering transformations not from past to future, but like if you think about, if you want to describe states evolving, let's say in some spatial direction, like a hypersurface, which is time-like, and push it this way, then the transformation from here to here need not be unitary, but, or if you choose different shapes. But all of this is described on equal footing, agreeing with this other approach. Now, well, this does not necessarily mean that this is the right approach. But it's one indication that it might be fruitful.
I mean, I think this evolving state sideways would also be possible. It's possible in the kind of in the operator tensor framework, and it would be possible also, I think, in the sort of time symmetrized version. But the other points you raise, I think, are interesting. I mean, all these points are interesting, but yeah, there's something to be understood. This is clear.
Okay, so let me play the role of the moderator. It's great to see that there are still so many people and such a tough discussion after 2 hours and a half, and there are still actually 2 people who would like to intervene. So first Marios and then Nicola Pinzani. So if you're not
actually,
tired, Lucien, then...
Yeah, I mean, it's been going a long time. I can also send an email. Depends on Lucien.
I'm fine. It's everyone else is
Okay, so it's a bit of a trick question that I also asked to Carlo. That I don't know what is the. I really don't know if it makes sense or not. So let me put it this way. What I don't understand in all of this discussion is whether we're discussing about interpretation or about what is correct or not empirically. And what I do not understand, I mean, not in what you say, what I cannot understand, I'm confused about, is the following, that I think that if I ask the question, do we have experimental proof that there exists signaling from the past to the future? I have the feeling that the answer is yes.
Yeah.
But I'm not sure if that's the correct answer. Why? Because if I ask the other question, do we have experimental proof that there exists signaling from the future to the past? I have no idea if this question is defined. And either both of them should be able to be answered empirically, or at least tested, or none of them. So I'm just wondering what is, if you have any thoughts on that. In other words, with what regards to signaling, are we talking about effects that are physical, or is this about interpreting the theory? Is this metaphysics?
I mean, the definition I give is a kind of formal definition that, if you have no information about the past, then you can get no information about some intermediate process in the future, and vice versa. And certainly in the backwards direction, that's not surprising. We don't have any information about the future, so it's not surprising we can't get information about an intermediate process in the past. But formally, the statement is time symmetric. So you're asking an empirical question.
I'm asking if in principle, in your opinion, if in principle there could be even a thought experiment that would prove that signaling from the future to the past exists.
Can
I jump in?
Yeah, please do, Carlo, because
imagine a space-time situation in which nothing happens, and there are 2 points in space-time, A and B, and there is something connecting A and B, some disturbance in the water connecting A and B. Okay. And the extreme of this, A and B are 2. So is A sending a signal to B, or is B sending a signal to A? That's the question. Okay. I haven't told you which one comes first. Well, I need a definition of what it means to send a signal and what it means to receive a signal. Okay. Otherwise, your question, it cannot be addressed empirically. So I need a definition of what it means to send a signal. Now, what it means to send a signal, it means that I am free to decide something about my future and not about my past. Okay? So if I assume that there is an in A, in the space-time region A, something, somebody, somewhere, some whatever, that can make a free choice, but in the definition of free choice, there is a breaking of time reversal invariance, then I can address the question, but the question is already answered by the definition
By
of sending.
assumption.
And so, the question physically, I mean, there's a part which is just definition. Physically, it's reduced to what are we talking about when we talk about somebody deciding? And that's a very tough questions because which can be addressed. I mean, a machine that takes a decision can be described, but to address it, it requires much more than the physical laws of quantum correlations, or it requires the actual dynamics of the thing we call deciders, where is a man or a cat or a computer that at some point pops up something. And if we do that, it seems to me we are doing the physics of these complicated systems, and we definitely are talking in thermodynamical terms.
So are you saying, though, Carlo, that we do not have experimental evidence of signaling from the past to the future? That it's by assumption that we put this in the theory?
I think that it's a part with just definition, and when we test the fact that we cannot send signal into the future, we are testing something about the macroscopical existence of things which we call deciders, which take a decision. And so we're testing something about the macrophysics. We're testing something about the non-time reversal invariance of the macrophysics. I mean, it's if I throw a pencil in the water, I see immediately time reversal, breaking of time reversal invariance. And that's the kind of things, and a pencil falling in the water is sending a signal out in terms of waves moving out. So we're calling that sending a signal, and we're giving this name to a phenomenon which is breaking, which is a macroscopic dissipation phenomenon, which we describe in terms of macrophysics, of time reversible macrophysics.
Yes, I see what you're saying. I'm trying to get my head around, I guess, whether in a time symmetric formulation, what you want to see is signaling in both ways, or basically you drop the notion of signaling and you talk about correlations between.
There's no meaning of signaling, unless you bring in the rest. There's no fundamental meaning of signaling.
Yeah.
I mean, there's a meaning of correlations, of course. If this, then that, and if that, then this. So this is very much in the fundamental theory. Fundamental theory is telling me that if a wave is going that direction, it will go there, and if it was coming from that direction, it's come from there. So that's the dynamics of wave by itself is time symmetric if you disregard dissipation.
Okay, I'm satisfied. I can leave my time to the next.
Nicolas.
Thanks.
Okay, thank you for the very interesting talk. So I was just wanting to raise a point about the framework. So I don't know if you like you were talking about describing this kind of classical dynamic as classical wires of knowledge that kind of propagates.
Yeah.
Like, for example, there is the framework of categorical probabilistic theories, which is formulated exactly in those ways. Like, instead of having a kind of an operational theory where classicality is just an index, it kind of labels something. It is an actual system, and then you're interested in the correlation between inputs and outputs, or if you want, you can just take the unital operations and then see classicality inside the correlations. But well, there is already a framework which is able to talk about kind of like classical dynamics at the same time, like together with a kind of dynamic of kind of quantum boxes and quantum operations. But so yeah, it may be interesting to kind of map it to that kind of research and the direction of study. Yeah, what I was interested in understanding is that in those framework of categorical probabilistic theories, you can understand the kind of notion of application of a quantum box as the knowledge that an actor or someone has that a quantum operation has been applied. You know? And and this kind of resonates with Bohr's perspective that, okay, we need to know the kind of causal structure of experiment to assign probabilities to an experiment, and that this kind of classicality of causal structure is an a priori requirement of the understanding of the theory, because you need to know how to plug boxes together and all those kind of things. But we may think about a kind of situation where the knowledge about the order of the box is unknown, and so you would have certain type of correlations that would emerge from this kind of output-input perspective.
Yeah.
Okay, of course, this is not assuming that you have that you are starting with flat distributions, but you're reading kind of correlation, like you're leaving all the wires open in a sense. But I don't know if you have something to say about this kind of the idea of kind of internalizing the notion that the application of the boxes can be stochastic inside the theory itself, or even kind of quantum indefinite. But then, because this, for example, this is a recent work that I tried to do in a paper. I don't know if you have any thoughts about this.
Just while I remember, please send me a copy of that paper if it's out. So at the beginning, I mean, I think definitely this kind of categorical approach is a way to do it. So I think it's not difficult to sort of apply that kind of framework to the situation I was describing. I think what will be interesting is those boxes that appear, the classical boxes, should also respect the conditions that I've imposed. And I think that when you make them respect those conditions, it will be interesting to see what happens. So I think that's where the new results will come out. In terms of indefinite causal structure and time symmetry, I haven't thought about it a great deal, but when I answered Robert's question much earlier, I was talking about the quantum equivalence principle, which is a way to locally have definite causal structure, even if globally you don't have definite causal structure. And in that context, you could apply these time symmetric principles. But the framework I have for that is not an operational framework. It's a different kind of framework. So there's some work to be done to bring those ideas together. And also work that's been done by let's see who I think some various people. So Onion and Philip are still here. They have this work where you get you have two different ways of representing the same physical situation, where a particular event in a circuit representation can get delocalized. You're probably familiar with that. So whereas if you go to a different circuit representation of the same situation, then that event is localized, but a different event becomes delocalized. And so that kind of framework that Onion and also Philip have worked on might be a place you could try to address time symmetry. So you can locally make an event. You can make an event by choosing the right circuit, which is a sort of a kind of causal frame of reference. You can make a certain event local, and then you can think about ideas of time symmetry. So that might be a way to do it. And but I haven't worked on it.
Like in all those kind of operational approaches, classicality emerges in the order itself of the boxes. You know, like it's you have some classical information about the kind of global structure of the experiment, which is constructed of boxes which connect sequentially, or so there is kind of an idea that you are taking classicality as a priori, kind of a necessity in that.
Yeah. I mean, definitely what I've described is very conservative when it comes to this kind of thing. You take the order of the boxes as being classical, and fixed, a fixed kind of background, and it's very conservative there. And there are questions there, like why should you allow, why should you allow yourself to arbitrarily choose the order of the boxes? If I don't allow myself to, if I'm being very careful about my incomes and considering flat distributions over incomes, why do I allow myself this freedom to consider to nevertheless put my boxes wherever I want? And so perhaps there are questions there you can ask. And this ties in with this distinction between setting and income that perhaps needs to be understood. But yeah, I don't have any good ideas about it. These are just questions.
Yeah, I mean, it would be interesting to link. I'm gonna send you the paper, because like what I try to do there is like to think about, like to internalize in this framework of categorical probabilistic theories, to kind of internalize the notion of kind of classicality. The agent classically knows about how the boxes are, classically disposed, and this can be given. This can also be kind of generalizing.
Okay.
It would be interesting to see the connections.
Good. So I look forward to getting the paper.
Thank you. Do some other people have comments, questions?
I would like to make a last follow-up comment. So, Lucien, are there more things possible in a time-symmetric formulation of quantum theory, more dynamics, or is it a reformulation of what was already there?
So it's a reformulation. There's nothing new. And I think this is also made very clear in the paper by DiBaggio et al. And the same was true, incidentally, in just like the original ABL paper. They just showed it was the same formulation. It was the same physics, but just there was a way to reformulate it to make it time symmetric. So as it stands, it's the same physics. Although there's the operational counterpart on the other hand. So a lot of the principles I discussed stand alone, away from quantum theory, and so they might enable you to discuss more general physical theories that are time symmetric and yet not quantum theory.
I see. So yes, so I mean, this answers my question, right? There is no way to empirically distinguish this as an interpretation unless you have some theory that is more general that you wouldn't be able to describe with a time asymmetric formulation. In other words, you are going to need some quantum gravity experiment.
Yeah, that's right. I think I see it as being, like often we have some physics and we don't understand it has a certain symmetry, and the way quantum theory is normally presented, it looks like it's time asymmetric. In fact, on the Wikipedia page, on the arrow of time, the time asymmetry of quantum theory is mentioned as one of the time asymmetries, and so just knowing theoretically that it can be made time symmetric, I think, is important. It's good to be able to find a perspective on physics that makes it symmetric in a certain way.
Thank you. So if there are no more people wanting to say something, then I think it's good time to close this session. Thank you again, Lucien, very much for your talk and for answering all those many questions. It was really a long time today. And thank you all for attending. And we will see in a month for the next QISS seminar. And next time it will be Czeslaw Bruckner, who's going to talk about some, we don't know yet. It will be some secret topic. So everyone, have a good day, have a good evening, and see you soon.
Great, thank you.
Hello, everybody. Ciao.
Ciao. Ciao.
Bye.
Thank you, Lucien.
Thank you, Lucien, so much.
Yeah, thanks for the questions and answers. Bye. Great. Okay, there we go. Bye.
Bye.